Today, we are going to be going over data structures. And data structures are, at its most fundamental level, just a way of organizing your data. So let's go ahead and kick this off. A quick review of what we went over yesterday, in terms of like what we would need to know for this lesson, is that when the computer saves values coming from your code, it puts it in place on your computer called memory. In this case, for many modern computers, that's going to be like your RAM. And when we put our values into memory, we talked about like the need to be able to pull values from memory and like stick that into like the CPU to like do some processing, right? But we never really talked about like, all right, like how do we go into memory to like grab values out? Because like we might save a bunch of like values, a bunch of like numbers, turn them into binary, stick them into RAM, and then like something happens that like we're able to like take those values and stick it into the CPU, or take those values and like bring it back to like the user. But like, how does that actually happen? And that's what we're going to be going over today, with understanding the concept of pointers, which we're going to go over lightly because we don't have access to pointers in JavaScript, and references, which are going to be the key part of like how we're going to understand why we went over like memory and like how that ties into what we're doing with like JavaScript when we're making references to more complex objects. Yeah, exactly, like addresses. Or if you want to think of it as an array, like memory just has like a list of like a lot of indices where you can use an index to get to that position. All right, so references and pointers. So some programming languages give you the ability to go directly to a memory location using an address or a pointer, which is honestly just a number. That by providing like some value to say like, hey, I want to go into memory at this position, the program will be able to access like exactly that, the memory at that position, to see like what data exists at that point. If you tried to do something along the lines of like access memory at some like random location, you might get some random value back, you might get nothing back. You just get back whatever is stored in memory at that location, whether it has to do with like your code or not, which has been like a major concern in terms of security for why like C or C++ has had like vulnerabilities in the past, specifically with like Stack Overflow issues, or like potentially like injecting like your own like particular memory addresses if possible. So yeah, that's just a brief tangent on like the idea of using addresses to access like different points of memory. But for JavaScript, we only have like the concept of references. There's no way for us to be able to provide like a numerical value and say like, hey, go to memory at this position and like grab me whatever value is at this position in memory. JavaScript doesn't allow that. JavaScript just lets you access what we call references, which are the blocks of memory or the blocks of data that already exist in memory. And you might be asking, well, what's the difference? And the key difference here is that pointers or addresses are the numbers that represent where the data is at, and references are the data that already exists in memory. So for example, if we go here, like actually it's gonna come up a little bit later down in another slide down here. So there'll be another example a little bit further down that shows an example of what exactly that looks like for having like memory addresses. But Sarah, you had a question?
Uh, yeah, I was gonna ask, like, did you say that it was like indices, like the references, the blocks of code, or am I misunderstanding that?
Oh, it's addresses or pointers that are like more like indices. And then the references are like the values in the array.
Okay, so the references are like the values in the array, and then the addresses are like the indices.
Exactly.
Gotcha. The only reason I found that confusing is because yesterday when we were talking about random access memory, you said when we're able to access something, it's more like an object where we can access the key directly rather than an array. But this is like completely different,
Could
right?
you repeat that one more time?
Like kind of like, but the analogy still stands. We're talking about like memory where it's more like objects rather than an array, even though we're still using like indices as like an analogy here. It's still more like an object where you can like directly access a key versus where you would have to loop through it like an array.
Yeah, exactly. Like the reason why like I bring up like arrays and like indices is because like you've got some value that identifies like where this data is at, and then you've got the data itself. So in the same way that like with an object, you've got a key which corresponds to a value, where the key would might be the odd address. Same deal like an array, where like you have an index that corresponds to the value associated with that index. Same deal for memory, that you've got a memory address, and when you access memory using that memory address, there's some value that's corresponding to that like address.
Understood. Thank you.
No problem. Angel?
Yeah, I just want to make sure I get the distinction correct. So pointers and addresses is like directly I shouldn't use the word reference, but directly being able to access the memory location, and a reference is just that data is already there, but could you actually just explain it again?
Yeah, sure. In fact, let me scroll down to another example that I've got, I believe, here. So for example, yeah, this is a little bit further down, but think of it as like these in the pointy brackets would be the addresses or the pointers, which are just represented by a number. And then next to the addresses are like the actual value that's corresponding to that, like to that pointer or to that memory address. And so for example, here, if we had like this value of like 1 here, and then this next value stored a, let's say, a pointer to another value, that we would save this number right here, which corresponds to 120, and that 120 corresponds to the memory address of the next value. Does that make sense?
A bit.
So think of it as like this, like if we think about it in terms of like houses, right? Like you've got the house number, which identifies like which house it is, and then you've got the interior of the house, which like actually represents like everything inside of it. That like you can store the house number somewhere, and then you can use that to go to the house and then go into the house to access whatever you need. Where like inside the house would be the reference, and then the house number would be like the address.
Okay. So
right.
The reference allows you to kind of like view what's inside of it, and the pointer just points like to where that is in memory.
Exactly.
Okay.
Awesome. So going back here, all right. Yep, reference is the value and the address is the index. Yep, exactly. And we also do want to note that there is a difference between references and values based on what we've seen in JavaScript so far. You guys might have remembered the term like pass by reference versus pass by value. And the key distinction to draw between the two is that when we're talking about references, that when we provide a reference to something, that data is already in memory. Like say, for example, like if we provided a reference to an array, that array is already in like program memory and like it already exists there. And any changes that we make to the array that we're referencing changes the array everywhere else in the code. Whereas if we pass a value to like, let's say a function or like to anything else, that we're creating a new copy of the data. Like let's say if we're passing the value 3 rather than an array, that if we pass the value 3 down to like another function, the program is going to create a new space in like memory for another 3, so that like we have access to particularly just that number 3, even though like we might have another variable that stores like the number 3 somewhere else in like memory, and edits to the new copy of the data when we like pass it from like let's say one function to another or from one place to another. If we change that number 3 and we say like we want to change this to be like 1 more than it used to be, even though like now like we increased 3 to be 4, like when we use that value, it doesn't change the original value that we pass to like let's say the function. And I now kind of realize that it's a little bit weird to see without an example, but we'll be getting into an example of that like right further down when we start talking about nodes. So if you're not too sure about like what we're talking about here with like references versus values, it will make sense once we get down to like around like slide 7. All right. But moving on from there. So that's the concept of references and pointers in memory. And keep that in mind as we go through the concept of the data structure, because these two concepts are going to tie together. But to start with what's a data structure, like it says on slide 1, it's just a way of being able to organize your data. If you've got multiple different data points that are related to each other, you need a way of connecting them, right? Like, for example, if we've got like an array of 5 numbers, we want to make sure that these 5 numbers are associated with each other. So that's why we have them in an array and we line them up right next to each other. If we've got an object, we've got a key and a value, and we want to make sure that these two things are lined up together. So using an object allows us to line up a key with a value to connect these two values together. And then another data structure that we've used before in class is a set, which is just a data structure that makes sure that anything that you put into it is unique. And these are all data structures that we've used before as part of class, and they definitely have their like use cases, and they're great for like certain things, but they're not good for every use case. And we'll go over more different use cases on what things are good for, what things are not good for, like as we move like further along. But these are just some examples of data structures that we already have experience using. All right. And we can use those existing data structures to actually build out more complex like data structures, or at least data structures that follow specific rules. One particular data structure that we can implement using just the standard structures that we have in JavaScript is, for example, a stack. A stack is a data structure that has particular rules about how data comes in and exits the data structure. And those rules are that when you add a value, it should go to the top of the list. And when you remove a value, you can only remove it from the top. And you can only see the top value at any given time. These are some rules around like what we call a stack. And that's helpful in certain situations. Like, for example, if we wanted to process if we had a priority set of like, let's say, documents that we wanted to go through, and like the newest incoming document was always going to be like the most important one to process. Before I move on to showing you guys an implementation of that, it's important to note that a stack is known as what we call a FIFO structure, and that stands for first in, first out, meaning that the first value that we put into the... Oh, never mind. Last in, first out, excuse me. It's a last in, first out structure because the last item that we just put into the structure should be the first thing that comes out of that structure. That if the latest value that we put in, like according to this example here, is the value 6, then 6 should be the first value that we pop off because it's the last thing that we put in, so it's the first thing that we should take out. And Will, you had a question?
Yeah, I was just trying to think of some real world examples that represents stacks, and I was thinking of putting money or taking money out of my bank account.
How so?
Because I was just thinking, because there's whatever I have in my bank account represents a value, and the value is the amount of money that I have there. Mm-hmm. And then when I deposit money, it changes the value that's within my bank account.
But that could just be done by just doing like another mathematical operation, no?
So I'm just trying to, when it comes to data structures, math doesn't really play a role.
Not in particular, because like data structures, the key concept around that is just how we're organizing data. It doesn't necessarily have to do with like how we like perform manipulate. Like, but it's like right. The key part of it is just like how it's organized.
How the data / information is organized.
Exactly. And got yeah, it. And just from Googling it, it gave me a pretty good example. Like this is something that all of you guys have experience with. Like, for example, the history of like visited websites. That if we go from like page to page, like think of it as a stack where like we started from like the main page, like the main like Google landing page, or the Google Chrome landing page, and then we went to google.com to search for real world use cases of stacks, right? So what that did was under the hood in the browser, it took the next site that we were going to, google.com, for like this this particular search. We put it on top of our search history. So now this is sitting on top of our stack. But now if we were to click the back button, what that did was it just popped it off of like the top of the stack to go back to where we were previously. So if we were to go to, let's say, google.com, and then we go to reddit.com, and then we go to like facebook.com. Oh God, I'm logged into Facebook. Get out of here. All right. So we were able to when we put the last value of Facebook on, like we put that on top of our stack. And then when we hit the back button, we pop that off of our stack to get back to like where we were previously. And now if we hit the back button again, reddit.com is now at the top of the stack. So we're popping it off and we're going back to google.com. And if we go hit back one more time, we're popping google.com off of the stack to get back to the original like Google page. And yeah, Angel's got a great example here. A good example might be a stack of papers you have in front of you. Within the rules of a stack, you can add a piece of paper on top, and then when you remove a piece of paper, you have to remove it from like the top of the stack. And you can only see the current piece of paper at the top. Exactly.
So stacks is just a way to structure data.
Exactly.
Got it. Cool.
And yeah, now that we have like a general concept of what a stack is, let's see exactly what that looks like in code. So if I were to go to our terminal here, C, ls, cd into, you know, make your DSA, cd DSA, and we'll touch we'll touch stack.js. And we'll code dot here. Come on. There we go. Oh. Yes, I trust the authors. I am the author. Okay, so for a stack in particular, let's say, what we could do is, let's say that, we'll go ahead and use a class for this. Class stack. To constructor. Oh, well, thank you, AI. Yeah, so this would be some example code for what a stack would look like. That you'd have we've gone over classes before, but we'll also do a little bit of review like in a later slide. But we would start with saying like, whenever we create a new stack, we're gonna start off with an empty array to keep track of our data. And whenever we push new data into our stack, we're going to put it onto the end of the array that we use to keep track of our stack. And whenever we remove an item from our stack, we just pop it off the end of our array. And finally, if we want to see the current value on the top of our stack, we just look at the last value in our array. And so if we were to do something like const my stack is equal to new stack, and then we were to say my stack.push1, console.log, my stack.peak. And then we do my stack.push2, console.log, my stack.peak. Should be 2. Should be 1. And then we do my stack.push3, console.log, my stack.peak. Should be 3. My stack.pop. And if we console.log, it should be 2. And if we do my stack.pop, it should be 1. And if we pop it again, and we do peak, it should be undefined because we would have nothing left inside. So let's go ahead and run this real quick. If we go to terminal, new terminal here, and we were to node stack.js. And there we go. we can see that when we do myStack.push1 and then we peek on the stack, we get the value 1 back because that's the topmost value on our data. And then after that, when we do myStack.push2 and then we do myStack.peek, we should expect to see 2 because that's now the value that's at the top. Then after that, when we do myStack.push3 and we console.log myStack.peek, myStack.peek should show us the last thing that we put on top of the stack, which is 3, which we can see right down here. And then after that, when we do myStack.pop, and then we look at the top value again, we should expect that 3 is gone, and we should get back to what we previously had on top, which is 2. And when we console.log that out, we do in fact see that we got a 2 here. And then when we do pop again to remove the 2, which is currently at the top of the stack, we should get back to 1. And in fact, there it is. There's the 1. And then finally, when we do myStack.pop on that last value of 1, there should be nothing left in the array. So if we do myStack.peek to try and see like what's at the top of the stack, we should get undefined or like maybe throw an error here, which we can add some code in here to do that. Like let's say if this .data.length is equal to 0, we should, let's say, let's throw new error stack is empty. So if we try that out, now we can see that if we try to do peek on an empty stack, it's just going to throw an error and say like, hey, the stack is empty. You can't do that. Any questions on the concept of a stack so far? Relatively self-explanatory, like makes sense, like completely lost, like how are people feeling so far? Sarah?
Could you explain if you could go through like the kind of when you were like console logging it?
Any part in particular? Like just each like go through all of this again.
Just the last 2 of how we got back to 1.
Okay, cool. So once we push all our values on, right? Like think of it, let me draw this out. So when we do myStack.push1, so then our stack has 1 inside of our array, right? And then we do myStack.push2. Because we're putting it on the end of the array, we can think of it, if we look at it from a top-down view, of 2 being on top of 1. That we're pushing 2 on top of 1, so 1 is going to be the last value, and 2 is going to be like the topmost value as the last value within our array so far. Then when we do myStack.push3, we got a 3 over here, which puts it on top of the 2. But then when we do myStack.pop, what we're doing is we're getting rid of the topmost value. So what we'd be doing is we'd be getting rid of this 3 right here. Oop. And so if we take a look at the stack again after we've popped our value of 3 from this part right here, it should be 2, which is our topmost value at that point. And if we do myStack.pop again, 3 we already got rid of. So we're going to be popping from the top of our list, which is at this point 2. So boop, we get rid of 2 and we console.log stack.peek. And at this point, it's going to be 1. And so if we do pop again, our current top of a stack is 1. So boop, we get rid of that. And so if we console.log myStack.peek now, it should throw the error of, hey, like our stack is empty because we have nothing left in our stack. Does that make sense?
Yep, that absolutely makes sense. Thank you.
Awesome, no problem. Angel?
Is this how undo and like redo functions are done in like, like text applications or anything like that?
I believe so. I haven't worked on like any text editors in particular, but it would make sense to consider like, hey, like every change that you make on a document, we push that onto a stack. And if you wanted to Command Z that, you could just pop that from the stack to get back to like the previous position where you were at. And similarly, like you could Command Shift Z to add those values back onto the stack if like you wanted to undo your undo. Does that make sense?
Yeah, makes perfect sense.
All right, awesome. Cool. So that is a stack. Let's go ahead and clear these drawings here. Okay. So close the annotation menu and let's go back to Chrome. Okay. So that's one example of a data structure that can be implemented using just more like relatively simple existing data structures. But there could be more complex data structures that you want to implement. For example, trees or graphs or what have you. And the structure that we just looked at for stacks are sequential or linear, meaning that they're lined up in memory. But there may be cases where like you don't want that to happen. And we'll get further into that in like a later slide, but like there may be cases where like data isn't like all lined up like together, like one after the other. And like you do want to be able to like connect different points, even though like they're going to exist in different points of memory. So that's why we talked about references at the very beginning, like slide, to say like, all right, like if we want to be able to tie like one particular data point to another particular data point, even if they're not going to be like right next to each other in memory, references are going to be our way of being able to do that. And in order to be able to use like references in terms of like keeping track of both like a value and like the next value that should be associated with this data point, we've got to use this idea of a node, which you're going to see a lot of with like linked lists and like graphs and trees and all that. So for example, here we have an example of a tree. This is a binary search tree. And within this tree, like each node here is a circle. And each circle here has a value and then two connecting points that connect it to other nodes. So for example, this node with the value 4 in here has a value of 4, and it's also got references to two other nodes. And if we follow those references, we can follow it to another node, which will have a value and possibly other references to other nodes. So from this node of 2, if we follow the references for 2, we can go down to 1 or 3. And if we go down to the node with the value of 1, we can see that there are no more references here. So this node is an ending point. It's I believe the term for the end nodes on trees were called leaves. So this would be like a leaf on a tree. All right. So to go a little bit further into the concept of what a node is, again, it's just another container for data. Like it keeps track of potential values that you want to save, and it would keep track of however many like connections that you would want to make from that particular data point to other data points. And the easiest way to represent a node is with an object, where if we go back to VS Code here, and we create a new file for a node.js, we could do something like const node is equal to value, like let's say 1, next is going to be, before that, const 2 is equal to value 2, next null, next is going to be node 2. So that way we could do console.log, node.value, console.log, node.next.value, save that, go back here, run node.js here. And we can see that if we have a starting node here that has a particular value, we can get the value out of that node. And we can also follow the next value on this node to get to the next node, which is node 2. And then when we go to the next node here and we see the next value here, we can see the value and we can see that next is null. So that's the ending point. And if we were to further expand this example out a little bit more, const node 3 is equal to value 3, comma, next is null. And then here, value 2, and the next here would say node 3. And instead of just like hard coding, like, hey, we just go to this node and then the next node there, we can say let current node is equal to node, while current node dot next, or actually just while current node, console.log current node dot value, and then current node is equal to current node dot next. So if we save that, run it again, now we can see we got 1, 2, 3 with the code that we have here. Because we're starting with creating a reference to this object here using current node. Because remember, when we assign a variable, like when we assign an object to a variable, we're assigning by reference. So we're going into the memory that contains this object, and we're saying that this this variable points to this data that we already have in memory. So while our current node actually exists, like while there is actually data in our current node, we're going to take a look at the value that's in our current node right now. And then we're going to say that our current node is going to point to a different node. It's going to point to the next node that our current node is keeping track of. So by doing current node is equal to current node dot next, all we're saying is we're updating current node to be this next node, node 2. So once we hit node 2, we do node 2 dot value, and then current node is current node dot next. Since we're currently on node 2, we're updating current node to be the next of node 2, which would be node 3, which is how we get to 3 down here. Sarah?
So the while loop is basically making it so that current node, which is pointing, so when we assign a variable, we're just pointing to like the reference to something.
Particularly for objects and arrays.
And okay, so then when we're assigning current node, we're just saying like, this is like what the current node is, and as we're going and that node is changing from as we're going through each node. So from like the first one to the second one to the third one. So current node is changing, going through each one of those things. So is that correct?
Exactly. And that's what this step right here on line 20 is doing for us.
Gotcha. And the other question I had is kind of going a little bit back, but like I remember when you said that like we have like references in memory. So like we have like references in memory, but then variables are like, for example, like the difference between an array and the number 3. So does the number 3 not exist in memory then? If it doesn't, then where does it exist?
It does, but the key point to make here is that when we do something along the lines of like let x is equal to 3, and then if we had like function print number and it takes in a number, and we console.log num, versus if we had let y is equal to 1, 2, 3, and we do function print array console.log array that so the value, like this is a distinction between passing by value versus passing by reference. That when we say, for example, down here and we do print number x, and then down here we do print array y. By doing print number x, num here is going to be a completely separate copy of x. Because if we did like, let's say plus plus num, and then here we did array dot push, let's say 4, and then we did print x here, or console.log x here, and then down here we did console.log y here. Save that. We'll run Node.js. We can see, and let me go ahead and comment out the while loop here. So you can see when we do print number x here, we get 4 when we console.log num here, right? Because we added 1 to num and then we console logged it out, and that's going to give us the number 4 because 3 plus 1 is 4, right? But when we console.log x, like right underneath, we still see that it's 3. Because while the number 3 does exist in memory, what we're doing when we're taking this number 3 and giving it to another function is we're creating a completely separate copy of this value that this function will have access to. So what we're editing when we do plus plus num here is we're editing the like the copy that we pass to this function, rather than like the value that exists outside of it. Whereas like with an array, we have to pass like more complex data structures by reference. So this array here would be y up here, because when we do print array y, we're passing a reference to this array down to this function. So any changes that we make to this array make changes directly to the array that we have in memory. So because we're making changes to the same array in memory, y is pointing to the same place in memory as this array is over here. So because we made a change to array in this function, that the same changes are going to be reflected inside of y here, because they're both the same array. They're just pointing to the same location in memory. So any changes that we're making in one place will change the other place as well.
Gotcha. And is that why, like, for example, if you do const array, you can still, like, even though you're doing const, which is like you can't change something, you could still push to that array, but you can't change like const like x equals 3?
Exactly, because like the const array would be a pointer to the array in the memory location. But if you tried to change it to a completely separate array, you'd be trying to update like the memory location like that variable contains. And that would be a no-go, because like then you would actually be changing like the actual value of like the array, right? Like the actual value of like the let me figure out how to phrase this. You would be changing the reference. Yeah, you would be changing like the array that you're referencing, because like you're no longer like pointing to the same array that you had in memory. You're pointing to a completely separate array now.
Understood. Thank you so much. Appreciate it.
Yep, no problem. Angel.
So can you scroll up a little bit?
Yep. Which part?
So wait. Oh, sorry, just line 24. So if I'm getting this right, then when we're printing on line 26, we're effectively saying num is pointing to x, and then that's how we know that it equals 3. But when we're using the array knows that the place in memory where y equals 1, 2, 3.
Yeah, like if you take what you said for the first function and applied it to the second function, I think you'd be correct.
Okay.
Because, for this function over here, this is pointing to this array. So that's how we know these are referring to like the same like array that we have in memory. But for this function up here, it's creating a completely separate copy of what we're already storing in X, specifically for this function. So that's why like when we make a change to num, it doesn't change X.
All right, thank you.
Yep, no problem. All right. Any questions on references versus values here so far? Any more questions? All right. So we had a look at just representing nodes using objects like this, right? And that's like a relatively simple way of doing things. But at the same time, like it's kind of cumbersome to like have to create like a new object for each of these, right? So one way that we could sort of simplify all this is, let me go ahead and take all this, comment it out. And let's go ahead and create a class node. And this class is going to take a constructor, which is going to have this dot value as value, and this dot next is going to equal to null. And what we can do is we can say, actually, that's all we really need for the node. Like all a node really keeps track of is the value and the next variable. But if we wanted to create a more complex data structure with this, we'll have a look at how to do that in the next slide. And for now, we're just going to export default node for now. So with that there, let's go back to the slides here. All right. So yeah, so let's talk a little bit about what a node in memory looks like when it sort of looks like this class right here, where we have a constructor, which is going to take in a value, and we have like a value lined up with this dot next, which is going to be a reference to potentially another node. That the way that works is traditionally you've got your values first and then memory addresses that link to other nodes. So with the example that we just did, well, not here, but over here, with const node 1, like node 2, node 3. This direction. We can represent that in a diagram just like this, where we've got node 1, which has a value of 1, which points to node 2, which has a value of 2, which points to node 3, which has a value of 3. What that would look like in memory is, for example, if we started with node 1 at position 64, let's say, that the computer like tried to figure out like, hey, like we need a place to put like this data into memory. All right, let's start with like position 64, because that was like the first like location that we could find. So we would have the value of 1 as the value at position 64, and then right after that would be a pointer, or at least in memory it would be a pointer to the next node at position 65 here, which is 1 more than 64. This would refer to, hey, like this is where the next node is going to start. So if we follow this memory address here, we would go down to 120, which stores the binary value for 2, which is right over here. So now that we can see the value, the next step, the next value in memory would be the reference in memory to the next node, which is the node with the value of 3. It just so happens that the node with the value of 3 got stuffed into a place above node 2 in terms of memory, because like maybe something happened on the computer that cleared up like that space in memory. So now we have access to it. So here with this value of 2, we take a look at the next value on this node, which points to position 4 here. So because this points to 4, we can see the memory address 4 here has our value of 3 inside of it. And yeah, if we were to print the value here, we would be able to see 3. And if we look at the memory address for node 3 here, we see that it's all zeros, which means that our node with the value of 3 does not have any next values, meaning that like this is our stopping point for 3. Any questions on how nodes are organized in memory, like having looked at this, or like, yeah, are there any questions? Sarah?
The first question I have is constructors are functions, right?
Yes.
Okay. And then like, so the first part, the first line is the node, and then the second line is the next one, or the address of the next one, is that?
Yeah, exactly.
Okay, got it, thank you.
Yep, no problem. Carlos?
So like this is kind of more an observation than a question, but the way we're seeing it here, those positions, those would be indices, right? And then the way the specific number is being written out is how we were talking about yesterday in binary, right?
Yep, exactly.
Got it. Awesome. Just trying to see how like it all starts connecting together. And I think you got some things in chat.
Oh, let me check chat real quick. Oh, yeah, I can run through that again. And each node should connect to another, and it should be that node in the object plus the link to the next. Each node should connect to another. Yes, you can create nodes that are off on their own, but like they just wouldn't be like useful. And it should be that node in the object plus the link to the next. Generally speaking, yeah, like nodes contain a value and a reference to the next node. So yeah, like that would be like what each node contains. And yeah, sure, I can run through this again. So if we were to start from like our first node, right? Like let's say like we had some code that was, let me annotate this out. Suppose that we had let first node equal to new node at 1. So if new node at 1, if we created a new node with the value of 1 here, right? What under the hood, the computer is going to look at, hey, we want to create a new node, and based on the code that we have in VS Code here for, oh, wait, why can I not scroll down when I'm using the annotate? So we want to create a new node. We're providing it a value. So we're assigning this dot value to be the value that we gave this node. And we're starting it off by saying this dot next is equal to null. Oh, here we go. Wait, where's the thing? Okay, I lost the zoom bar. Hang on for a second. Yeah, Carlos.
Oh, sorry. I don't know why my hand didn't go down.
Gotcha, no problem. All right. But yeah, based on our definition of a node here, we can see that we're going to have a value and we're going to have a next, right? Where this next, in terms of like what's happening under the hood, is going to be a memory address that points to where our next node is going to be. So if we had some code that looked like, and actually let me just go ahead and do this in VS Code, that if we did like let first node equal to new node with 1 here, let second node equal to new node 2, let third node is equal to new node value of 3, and then we did first node dot next is equal to second node, and second node dot next is equal to third node. By running this code right here, this would set up a data structure similar to what we see right here, where the node with 1 is first node, the node with 2 is second node, and the node with 3 is third node. When we set up a first node here, we already have a space for this dot value and this dot next. So if under the hood, the computer said like, hey, like we're going to put the first node right here, that this would start off with the value of 1, and this would be all zeros initially, up until the point where we do first node dot next is equal to second node. If we did first node dot next is equal to second node, and this node is already loaded into memory, then what we're doing is we're saying like the first node dot next is going to refer to the second node, which means that first node dot next is going to, in terms of like what's happening under the hood, it's going to store a pointer to the next node, to where that node exists in memory. And JavaScript is going to handle the heavy lifting of like turning the values at that position in memory into another node for you, so you don't have to worry specifically about like the pointers. But it is important to understand that when we're doing this, we're saving the position of where that next node is going to be at. We're just saying like, once you have this value, this is where you go to get the next value. And then once we're at the next node, here's the value for this node, and here's the place that you go to get the next value that's in our list. Elisha, does that make sense, or?
So so the 3 dots under, like what are those? Are those like going to the next node?
Oh, those are just like spaces, because like you could potentially have like a bunch of like different memory like in between. Like let's say if you had like a bunch of different variables that store like numbers and strings and all that, it's not absolutely necessary that all these nodes are lined up next to each other, so long as you have a way to get to the next node. And the way that we get to the next node is just by saying like, here's the location in memory that you go to get to the next node. But any like the dots represent like memory that could be like basically anything.
Gotcha. Okay, I understand it a little better now.
All right, awesome. Is there anything else that's unclear that could use some explanation on this concept of nodes? Anyone else have any questions? Sarah?
So that second line represents the address. So the address is represented as binary. So that's like a number. The number represents the address, which
Yep.
is.
All right. Any other questions from once? Can we do some code magic to make all the nodes link automatically? Technically, well, sort of, kind of. It's like, this is where data structures come into play, because a node on its own is just a container for data. But once we have containers for data, now we want to figure out how to organize those containers. And that brings us to our case study for linked lists. And a linked list is a collection of nodes that are linked together, and we should be able to add a new value to the starter list and remove a value from anywhere in it. And if we take a look at how we can use this concept of a linked list with nodes, let's take a look at some code that like lets us do that. So let me go ahead and clear off this annotation here. They're all drawings. Okay, so far in node.js here, we've got this class node, and we can go ahead and get rid of these for now. And then we're going to export default node so that we have access to use this. But if we go over here, create a new file, and we'll call this linked list.js. And then inside of our linked list here, and let's go to Node.js, save that real quick. And inside of linked list.js here, what we're going to do is create a class, linked list, take a constructor, and this dot head is equal to null. And I'll explain a little bit more about what this dot head is like once we're finished up with this. But if we want to say add value, then yeah, that looks about right. But let me go ahead and comment this code out like piece by piece. So here we're going to add a new node to the end, let's say to the beginning of the list, or create a container node to hold our data. And add is going to take a value. Here a node is going to take a value. If we don't have any nodes yet, set the first node to be the one we just made. Otherwise, and actually let me put this on a separate line so it's easier to comment. If we do have nodes, then what we're going to do is rather than loop through to get to the end, we're going to do, and we're going to change this code up a little bit. And we're going to do node.next is equal to this dot head. And then this dot head is equal to node.next. Set the next value of the node we just created to be the first item in our linked list. Set the first item in our linked list to be the node we just created. Oh yeah, and let me go ahead and send a link to the slides. Go here. Share. You know what? Anyone with the link. It's whatever. Copy that. Go to Slack. Go over here. Move this out of the way. Move this out of the way. Here's a link to the slides. So with the add function that we have here to add a new value into our linked list, what we're doing is we created a new node that's going to hold our value. And if we currently don't have any nodes in our linked list, then what we're going to do is we're going to say the first value in our list is going to be this new node that we just created. Otherwise, if we already do have nodes in our list, this node that we just created, we're going to say the next value of this node is going to be what's currently at the top of our list. And then we're going to say the top of our list is going to be the node that we created. So let me go ahead and draw that out for you guys. So if we were to say, draw it out. So we start with, let's say, our empty linked list here, that this box contains our linked list. That if we don't have any we don't have any nodes at the beginning, then what we're going to do is we're just going to create a new node here. And this node is going to have a value of, let's say, 1. And we'll also draw a line here, because that's how we represent a node in the linked list. So we've got this node of 1 if we were to, let's say, just add 1 into our linked list. But if we wanted to add another value after, and actually let me move this over here so we have a little bit more. Come on. I just had it perfectly straight, and now whatever. Why can I not move the? There we go. And God, this is annoying. Draw a line. Draw a line. Draw a line here. Select this. Move it over here. So suppose that we started our linked list with a node that just has like a 1 inside of it. And that's representing this. If this dot head is equal to null, then this dot head is equal to node. Where draw an arrow right now. So click on the arrow. So right now, this right here is our head. But if we wanted to add another value into our linked list to say like, hey, we want to add like the number 2 in now. If we want to add it to the front of our list, then our code down here for our else is going to help us accomplish that. We start with creating a node that has number 2 inside of it. So we draw a rectangle. So here's our node, and we're creating that node with a value of 2. And we're going to say node.next is going to be this dot head. So if we were to draw a line here. So we got that separated out. And then we draw an arrow, which represents node.next is equal to this dot head. This dot head right now is this node with a 1 inside of it. So this node with a 2 is going to point to this node with a 1 inside of it because this is the current head. And then after we do that, this dot head is going to equal to node.next, which means that we're going to get rid of this here, and we're going to say that this new node that we just created is going to be our new head. So what that did was it made it so that we could add a value directly in front of our linked list. And then we could just repeat that ad infinitum. Like if we wanted to create like a node which has the value of 3, we draw a new shape like so. This would be the number 3. Get a line here. Draw that line right here. And so this new node that we created, if we're adding it to the beginning of our list, would point to our current head, which at this point is now 2. And then we would update the head to be this value of 3 over here. Erase this and draw the arrow to 3. All right, Sarah?
So this dot head is the current node, and then the node that's pointing to the current node is the one that's like the next one, and then this dot head becomes the next node, and then so on and so forth.
Exactly.
Okay, thank you.
No problem. All right. Any other questions on this concept of adding new nodes into a linked list? And real quick, can I get a vibe check? Like, how are people feeling about this so far? Like, you get it, you don't get it. And yeah, we can take a 5 or 10. Well, yeah, we're already at 8 o'clock. Oh, Christian.
Hey Steve, I have a question about the else statement, right? Like underneath that rectangle.
Yep.
So we're trying to like change the header here. So I'm just trying to follow the code a little bit to see like how the head that head is like I guess being moved. So you mentioned that for the first on line 18, node.next, it was this at head. So what it's doing there is making the value next for to the current head, correct?
Yep.
Okay, so then in the case where we just start off with 1 and then we want to add 2, we're gonna point the next value for 2 to to the number one.
Mhm.
And
Or the
then
node that has one inside of it.
okay, yeah. So the node that has number one. And for line number 20, the next thing that we do here
Mhm.
is we're trying to figure out, or we're just trying to like change the head in this case. And it's gonna change it to node.next. And in this case, node.next,
Oh, excuse me. It's just gonna be node.
oh, okay, I get it now.
Yeah,
Yeah,
yeah, sorry about that. Sorry about that. If we
Yeah.
made like this dot head equal to node dot next, we would just be making it this dot head again. So sorry
Yeah.
about that. That was a typo.
okay. Yeah. All right, I got it. So that makes clearer
Alright.
now.
For sure, for sure. Yeah, sorry about that. Yeah, I can explain. Yeah, we'll go ahead and take a 10-minute break. We'll come back at 8:15, and then this like what we're talking about with data structures generally isn't used in like web development or in like front end web development. But like for the back end, like you may want like implementations that are more efficient for organizing your data. And I'll get into more detail around that. But in addition to being useful on the back end, like these are definitely some questions that may be asked of you in like encoding interviews as well. So just be wary of that, and I'll get into more detail on that like once we come back from our break. We'll be back at 8:15. All right, it's 8:15. Everyone back? Can I see a thumbs up if you guys are good to go? All right, I see a thumbs up here. Anyone else? Well, at the very least, I know Carlos is there. All right, Elisha's back. All right, cool. All right. So to answer some of the questions here. In terms of front-end programming, I've rarely had to use like data structures, if at all. In terms of back-end programming, I've had to use it like a handful of times. Like at my first like actual paid job, we were working with big data sets, specifically from data that we were scraping from public access websites. So part of working with data that's coming from like public access websites is like you get a lot of data that comes back, like even like hundreds of thousands, millions of rows. And we wanted to be able to like load all of those rows up and into our database, and like to be able to like pull those rows and like be able to access them, and then like send them over to like the client side. And then sometimes like we may want to add like a particular value in between like some of those like rows, right? And that's doable in JavaScript using just like a regular array. Like, let's say, for example, you've got an array of like 100,000 items and you wanted to insert a value into position like 50,000, or even at like the very first like element. And before I move on, let me go ahead and clear off the annotation here. And I actually have this in a drawing on another slide, so let me go ahead and jump over to that slide real quick. Over here, if we go down to why use data structures, right? Or not really a drawing so much as like just a way of showing like why we would like use this. That why would we use data structures? Well, key thing is like we want to get like the right tool for the right job. Like if you wanted to emulate like a line, particularly like let's say on the front end, to be able to say like, hey, here's the first node, here's the second node. When we remove something, we're going to remove it from the front, and when we like add something, we're going to add it onto the back. A queue would be a good approach to emulate that that sort of like structure. If you wanted to create like a social network, it'd be a really good idea to use a graph to represent like the friends that everyone has. Otherwise, like you might just have like, hell, I wouldn't even know like where to start, like if you weren't using a graph to represent like how people are connected to each other, right? Because like you would have it as like, hey, you have everyone who's friends with each other in an array, and then like people who are friends of friends, like maybe like an array within an array or something like that. That can get like really complex, and it can get really like troublesome to have to like update values for that. So having a data structure like a graph would be really good for representing those different connections from like user to user. Then beyond that, we also want to consider like performance. For example, when we add something to the beginning of an array, it's really expensive, like in terms of like time. Because what happens when you add something to the front of an array, that means that, for example, if in memory, we have an array that looks like this, right? And let's go ahead and add some memory addresses here, like 1, 2, and 3. Versus a linked list, which has, let's say 1, 2, 5, 6, and like 20, 21. All right. If we wanted to add something to the beginning of an array, generally speaking, when a value references an array, it references that very first element, or that position in the array that represents the first element. If we add something to the beginning of the array, what we basically have to do is we have to do 1, and then like let's say 1, all these zeros. But we can't have just this first value like override like the first value in the array already, right? Because like then we're just like updating the first value in the array to be something different rather than adding a new value to the beginning of the array. So we've got to push this first value down 1, which means that this value that was at position 2 needs to get pushed down 1, which means that this value at position 3 needs to get pushed down 1. And imagine if you had to do that for 100,000 like elements, that every time you add something to the beginning of an array, you have to push all of the other elements down in terms of memory to make space for that first element to exist. And now imagine if you had to do that like another 10,000 times on an array that already has 100,000 things. So that'd be like what, 10,000 times 100,000 like actions in memory just to add like 10,000 things into like the beginning of like an array that already exists. Versus if we have like a linked list here and we're trying to add something to the beginning of that linked list, then all we have to do is say like, hey, like it doesn't even have to be like in contiguous memory. It doesn't have to be like one right after the other. We could just do something along the lines of if we create a little bit more space here. So ... Suppose like we found some space at like position like 64. That like the value here is 1, 2, 3, 4, 5, 6, 7, 8. And then the next value there would be, let's say, at 1. And that's all we had to do. Like all we had to do was create one operation that added a new node in memory. And all we had to do was point that new node to an existing node that we already have for like our head value. So now this node becomes like at the top of our list, and it points to the first node that was previously at the top of our linked list. So rather than having to do like 10,000 times 100,000 like sort of like operations in memory, now we only have to do 20,000 operations in memory to write one value for the value and to write one value for like the next value. And that's a reduction of like, so it was like 100,000 divided by 2. That's a 50,000 time performance increase in terms of like number of operations. So that's why it's important to use the right tools for the right jobs, because if you happen to use like a data structure in the wrong way, you could be doing a lot more work, which would cause like a lot more time to be which would require a lot more time to be used to run certain operations. All right, Mikhail?
Is this like what you just described, like the linked version, like a slide version of the visual schematic you just described? Is this just the a literal, like us, you explaining it in a slideshow than what you just did the visual diagram of?
You talking about this? This right here, or rather,
With the
this
red,
right here
with
in
the
the linked list
red.
block? Good.
Okay, you did something with the red ink. I guess you were doing a draw on, and it was
No.
like a triangle.
You were talking about the squares and how they all like point to each other.
Yeah, it was like a triangle. Yeah, it was like yeah, and the squares were pointing to each other, but the first node, the second node, the third node.
Yeah, exactly. Like that's what this here represents in terms of like.
Okay, got it. Got it. Okay.
All right, let me see. All right, when should we consider our data structures when building out our algorithms/applications? It's an excellent question. Generally speaking, like you're going to want to consider like different like data structures or different algorithms when you've got a problem and you're trying to approach it in a way that, let's say, for example, like you have an understanding of the data that you're getting in, right? You understand like your input, which might be, hey, you have like 1 million rows of data that you want to work on. Or like you might have like 10,000 really complex objects that like that have like a bunch of like fields inside of it or something. And so you're going to want to think through like, all right, like number one, like what is the like fastest way to a solution? Like what's the happy path to get to from like point A to point B in terms of like just getting a solution out the door that works. And then once you have something that works, then you want to look at like the code that you just wrote for like, for example, like so for example, if we had create two, and let's say array add to top.js. Or let me rename that. Like, let's say if this was add to top.js, right? And so what we could do is, actually, can we do, I forget what the tools were for like doing benchmarking, but JS performance now. And do performance timing, performance now. Do something, performance now. Okay. So suppose we go into our code and we do something like on start array is equal to that, and let's do const linked list is equal to the new linked list, like that. And let's make sure that we go here, export default linked list, save that, up here, import linked list from linked list, lowercase l. Cool. So then if we were to do something like for let I is equal to that, and do 100,000 items, const array start performance.now, start array dot unshift I, and then array end, and then const linked list start performance.now. For that, we do linked list dot add, and we did say that as add, right? Yep. And then we do const linked list end is equal to performance.now. Then array time is that, and linked list time is that. Save that. And if we were to run node add to top.js, oh, not use, so we do have to use require. So in here, actually, you know what? npm init -y create me patch.json, please. Thank you very much. Go over here. Add to type module. Thank you very much. Go back here. Let's run it again. It's like module not So in our linked list JS, go up here. Import node from /node.js, and over here in at the top we'll import from linklist.js. Run that again. Oh, performance.now is not a function. That might just be in the browser. So maybe date.now. Oh, it's lowercase p. There we go. So let's check out the difference here, right? When we added 100,000 things to the beginning of our start array, that took us 788 milliseconds. When we did that for a linked list, it took us 4 milliseconds. That's a difference of about 200 times. And if we were to bump that number up even more by like a factor of 10, let's say, to 1 million items, save that, give it a run. It's going to take a little bit of time, like at least like 10, at a minimum, like at least 10 times more time. But the key thing to note here is that when you consider like the data that you're working with, and you consider the use cases of like what you're trying to do, having an understanding of like what data structures you can use to optimize your performance can significantly increase or like decrease the amount of time it takes to run your code. And as a result, it results in like your data getting passed back to like your user faster, or it results in like data that you're processing from your user faster, or any sort of like data processing task takes like faster. And anytime like we can reduce the amount of time it takes to do something, we want to attempt to do that. All right, while we're waiting for this to run, Sarah, what's up?
What you're illustrating here is the difference between like the data structure that's stackable versus not.
Not quite. This is just a different implementation of like how we could keep track of like data that's supposed to be in order. So for example, like if we had an array and we wanted to continuously add new values to the beginning of the array, like this code right here just shows us like, hey, like this is how we would add 1 million items to the beginning of an array, right? And it's like this compared to adding 1 million items to the beginning of a linked list. This is just meant to show like the difference in speed in terms of like if we had an implementation for an array versus an implementation for like a linked list. In case like, because like earlier we were talking about like step one, just getting it to work, right? Just getting it to be able to like add something to the beginning of the list. But if we take that like that very first like brute force approach based on like just what we know about like arrays or whatnot, like we would end up like waiting 82 well, is RDB seconds or milliseconds? I think these are seconds. Yeah, 82,000 seconds for 1 million items to be added to our array versus 68 seconds for 1 million items to be added to our linked list.
Gotcha. And it for both scenarios, it's adding it to the beginning, right? Where
Yep,
not.
exactly.
And the difference being is why again?
Yeah, so if we go back to the slide here, and then we go here, every time we add something to the beginning of an array, we have to push all of the other values in the array down by 1, which means that we have to rewrite all of these into a different like position in memory. And if we run out of space for this particular array, like let's say at 5 here, like do not touch. And like this will actually have a value, but like under the hood, the computer is going to be like, hey, this space is already taken. You can't expand the array to like to touch this part. So what the computer is going to do is it's going to try and find another place in memory to store all those values. And then it's going to rewrite all those values into that new position that like allocates that space for the array.
Gotcha. So it just pushes everything down by 1.
Yeah, it either pushes everything down by 1, or if it's like literally out of space, then it has to find more space in memory and then write all those values from like that one array to the new spot in memory.
Understood. And that's why there's so much time consumption for that one.
Exactly. Versus if we did it with just a linked list, all we have to do is find some space in memory and then link that up to like whatever is the first value right now, which is why we can see like it's way faster. Like even when like we consider, hey, 200 times more, if this is the case, then 10, 100, it's a little bit less than 200 here, but still it's a significant speed increase.
Understood. Thank you.
No problem. And then, yeah, Carlos.
So like yesterday we were talking about the interaction with the hardware and basically dealing within the ramifications of what the hardware allows us to deal with. But here, this is us being able to manipulate the data within the software, right? And I think I kind of want to jump off like where like Will was kind of heading to, if I'm correct in assuming this, but it's like, how is there a way to use this knowledge to better the way our like programs like run like even like faster than this? Like, is there something that we can make on our end to like make it run faster, or is this the limit right here?
It's a good question. Like, given what we have right now in our linked list, like this might be the ideal in terms of like adding something to the beginning of a list, because like if we analyze like the amount of time like this takes, right? Which I wanted to go over like time complexity like yesterday, but we ran out of time. So we'll just do like a brief like look at this. So when we're looking at time complexity, we want to figure out like how many things we're touching as part of like the code that we're dealing with here. Like, are we touching like all of the like what is this code depending on in terms of like the amount of time it takes to run it? And because like we can run through each line here, we can see const node is equal to new node value, That's O of 1, or what we call O of 1, constant time, because like it takes like almost no time to just like create a new value, to just find a place in memory and then create a node there. Then doing a check to see whether or not head is null, like that's O of 1, constant time. We're just checking, hey, is this null or not? This dot head is equal to node, that's just an assignment, no problem there. Else, no problem, node dot next is equal to this dot head. We're just saying like, hey, this next value is going to be another value, assignment, O of 1 time. This dot head is equal to node, O of 1 time, meaning that this add value, this add for linked lists here is only running in O of 1 time, constant time, in order to add a value to the beginning of the list. Whereas if we were to do this with a array, what that would mean is that we would have to move every value in the array down by 1, which means that if we have to touch every single value in the array every time we add something to the beginning of the list, if we consider that there are n values in an array, that means it's going to run in O of n time, which means that the amount of time it takes to add something to the beginning of the list scales based on like the number of items that are in the list. And O of 1 time means that no matter how many items we have in the list, it's always going to run in a constant amount of time. Even if we have like 100,000 items in our linked list right now, it's still going to take the same amount of time to add an item to the front than it would like if we had like no items in our like linked list. Whereas if we had like 100,000 items in our array, if we add something at the beginning of that, like it's going to take like some multiplier times like 100,000. Versus like if you add something to the beginning of an array with 10 items in it, it's going to be some multiplier times 10.
So can this kind of like, I don't know if it's a bad analogy or not, but it's almost kind of like when we think about like looping, right, or iterating through an array, right? Due to the fact that it has to iterate and touch every single index when we're using at least the array time here, that's why it's so slow. Because I did the math like between our last run, and like it's 1,215 times faster on that end between the 82,600 milliseconds versus the 68, right? So like is the reason being due to the fact that, and can you say that this is like linear, right? Or it's like linearly, maybe I'm mixing things up in my head, but since it's linearly like going through the array as opposed to like, let's say, jumping around or just going to certain specific points to iterate through that array, that is why it's slowing down?
It is because it's going through it linearly, but the key thing to note with the part about like jumping from point to point randomly is that when we're adding something to the beginning of a linked list, we don't actually have to jump like from point to point. We only have to create the first node, and then we already have access to like the first element in the linked list. So we don't have to like jump through all of the rest of them. We only have to have the first node that we want to add and the first node that we already keep track of, and then we just connect the two.
Got it. So just because of that connection, it's more instantaneous as opposed to having to linearly go through every single node.
Exactly. It's because we only need to make that connection to add it to the beginning. That makes it much faster.
Got it. Okay, thank you.
Yep, no problem. Yeah, Mikkel?
No, my question got answered. It's okay. Sorry.
All right, no problem. All right, cool. So that's an example with adding something to the beginning of a list. But then you also have to consider, all right, like what if we want to add something to the end of a list? So let's go ahead and add another function that would be able to add a value to the end of our linked list, given the structure that we have here. So if we have a function called add to end here, we take a value, and then we'll do const node is equal to that. And then while let current node is equal to this dot head, while current node dot next is not equal to null, current node is equal to current node dot next, and then current node dot next is equal to node. And then current node is equal to current node dot yep. And then yep. So what this will do is it'll try and run through using current node as like the current pointer to like to a particular node. And while we're doing like current node dot next is not equal to null, we're trying to move current node all the way up until like we hit the last node in our linked list. And then once we're at the last node in our linked list, we're going to say for that last node in our linked list, we want to say the next value for that last node is going to be this node that we created all the way up at the top here. So let me ask guys, how many values are we touching as part of this function? Yeah, Carlos?
So taking kind of a guess here, I want to say 1 to Will's 2, but I feel like I might be wrong here only because like we're talking about, is it a connection that we're considering as touching, or is it the actual nodes that are touching?
The actual nodes, like how many nodes that we like how many nodes are we touching?
Okay, then I think I'll agree with Will there. That's 2.
Current and next, not quite, because like the key thing to note here is that we're doing a while loop to go from current node to current node dot next, and we keep going until current node dot next doesn't have a next value, which means that, for example, with if we annotate here, and we do, where's the annotation menu? There it is. All right, we'll draw a square, go like this. And I'm not going to put values in here. I'm just going to draw the squares, and then I'm going to draw some arrows. So then in the shapes, we'll do an arrow to here, then arrow to here. So suppose we start with current node is equal to this dot head, right? So this is where current node is at right now. If we do current node is equal to current node dot next for the first time, where is current node now? Second one, exactly. So now current node is over here. And then is there a next value on this current node? Does it have like something that comes after it? Yep, exactly. So that means that we continue our loop and we do current node dot next. Our current node is equal to current node dot next. So once we run this line again, if current node is at the second value, where do we go?
The next node.
Exactly. Like we would go to the third one here. And is there a next value for this node?
No.
Exactly. So that's where we stop. And because current node is at this node right now, what we're saying is like, we'll add a node to the end of this node. So current node dot next is equal to node, which means that we're drawing an arrow here. And then our new node ends up at the end over here. So suppose we scale that out. Suppose that we had like 10,000 of these. If we had 10,000 nodes here, how many nodes do we have to touch to get to the end of it?
When you have to touch all 10,000.
Exactly. So that's what makes this O of n, because like it's dependent on the number of items that we have in our linked list. If we want to add something to the end for a linked list, that makes it so that like we have to go through every single node in the linked list before we can add something to the end of it. Whereas with an array, because we have that all loaded up into memory, if we just push something into the end of an array, then it's just finding a spot like in memory, like that's right after the last element in the array. There's no need to like push all of the elements down by one because all the elements are already in the right place. All we have to do is find a spot in memory to put that value into memory, and like that, boom, we're done. And let me show you guys what that looks like in terms of performance. So move this down here, clear this out. Yeah, Sarah?
Could you go through how many of the current nodes that we touched in again?
Yeah, sure. So if we were considering like adding something to the end of a linked list, right? Square here, square here, square here, right? Then we got arrow. So here, come on, give me the arrow. Where's the arrow? Arrow. What's going on? Arrow here. Okay. So suppose that we say current node is equal to this dot head, and this dot head is a reference to the very first node that we have in our linked list, right?
Yes.
So while current node dot next is not equal to null, meaning that while we don't have a node that comes after this, we're going to keep going, right?
Mhm.
So we're at the first node and we see that there's a next, which means that we're going to run this code inside the while loop, which is current node is equal to current node dot next. We're going to move the pointer here to say current node is going to now be like the second node. It's going to be current node dot next. We're moving it along.
Mhm.
And then because we're now at this node, we check the condition in the while loop again. Is current node.next equal to null? In this case, no, because we have something that comes after this. So we're going to run this line again. Current node is equal to current node.next, which takes us down over here, right?
Yes.
So now once we're here, is there a next value on this?
No.
Exactly. So because there's no next value on this, we exit out of our while loop and we say current node.next is now equal to the new node that we created up at the top at the beginning of this function here. Node is equal to new node with the value, right? So we're going to be creating a new node over here. New node. Come on, draw it. Zoom, what are you doing? Come on. There we go. So yeah, when we do current node.next is equal to node, we're just drawing another connection from this very last node that we got to a new node, which is why we have to touch every single value in a linked list to get to the end in order to add a new node to the end of it.
Gotcha. And so that's 4 in total.
Exactly. In this case, it's, well, 3 really, like because we go from the first to the second to the third, and then we add a fourth.
Yeah, a 4th. Okay, got it. Thank you.
Yep, no problem. And if we had like 10,000, we would have to touch all 10,000. Cool. So if we clear these drawings here, keep the mouse tool, go back over here, and let's go back to add to top.js, which we'll go ahead and rename this to perfcheck.js. And so now let's take a look at what this performance looks like if we wanted to add it to the end of the list. So here we'll do start array.push instead, and here we'll do linked list.add to end instead. We'll save that. And to start off with, because I don't want to wait too long, we'll just do 100,000 like values. So we'll run that. Oh, I cannot find module. Oh, node perf check. Give that a second or two to run. And now you can see like there's a major difference between like how long it took the array versus how long it took the linked list. Yeah, that like if we scroll up a little bit here, we can see that, hey, if we added something to the beginning of a list, linked list to add to the beginning takes 4 seconds for 100,000 things. Array took like almost 800 seconds for 100,000 things. But if we wanted to add a value to the end, arrays took 10 seconds overall to add 100,000 things. Linked list took almost like 7,000 seconds or milliseconds, I believe, to add all that to the end. So you can see like based on how you're using your data and like where you might want to do like your inserts or like where you might want to like add particular values, that using the right data structure can really help like increase your performance in terms of like what you're doing and ultimately just like get you your results like faster. But in order to do that, like you have to understand like what your inputs are, what you're trying to do with your data, and how to best model your data so that like you don't necessarily have to do like an excess amount of work in order to accomplish what you're trying to do. And that's why data structures are important, and especially why like once we get more into like algorithms, why picking the right algorithms would be useful in understanding like, all right, like how can we reduce the amount of time that this takes, or how can we reduce the amount of memory that we're using in order to like calculate this. Yeah, Carlos.
So is this how people like discover like functions like dot push or dot pop in a specific language, you know, because I feel like they would have to know this type of data in order to like come up with solutions like that in order to aid with people making things with the language, right? And so I feel like, is that why it's also very important to know this in order to find both, be sure which tools you're using for your data structure, but also possibly find other ways to make your data structure work faster?
Yes, although in terms of having your data structure work faster, with a lot of the data structures that we have nowadays, it's sort of like the question of like how far can we get with science, right? It's like with linked lists, for example, like you could make more incremental improvements on linked lists to make it like more performant in certain cases. And that really comes with like experience and like having a clear understanding of like how to potentially get like performance increases like out of like what you're doing, right? Because like if you get down to like understanding the base causes of like why something takes like super long to run. Like for example, like we now know like why it takes like super long to add a value to like the beginning of an array, right? And we know why it takes a long time for a linked list to add something to the end of an array, right? If we ask ourselves those questions of like, why does this take this long? Or like, why is this happening? We can potentially come up with solutions that help like mitigate like those issues. That like maybe we might not be able to address like 100% of it, but like we can at least like deal with like certain like cases for how we want our data to be processed, if that makes sense. Like, as an example, like, because like your question relates to how we can like potentially change our data structures to improve performance. Yeah.
Yeah.
All right. So it's like, for example, with our linked list here, if we wanted to make an improvement to our to adding a value to the end of our linked list, that is entirely possible with our linked list if we were to do something like this. This dot tail is equal to null. And then now once we have a tail, we can do this dot tail is equal to node. And otherwise, node dot next is equal to this dot head. And then this dot head is equal to node. And this dot tail is equal to this dot head dot next. What is it? No, this dot head. This dot head. Can we use this in front end components to make it render faster? I would not think so. Nah. Like it's only really because like even when you have like let's say 100,000 elements that you want to render on a page, you still have to pass all 100,000 of those elements down to React. Unless you're doing some sort of work to like add a value into that like array of things. Or like suppose like you're trying to edit like something within like that like data structure. That how do I put this? It's only useful if you're doing some data processing on the front end that deals with like big data or like is really expensive to run like on the data that you're working with.
Plus, doesn't your front end kind of just react to your back end, right? Like all this is processed by your back end, which is why I feel like we see this more on the back end as opposed to the front end.
Exactly. It's just a question of like, are you front loading the work onto the client or like, are you doing all of that work like directly on the back end? And if you are doing all the work directly on the back end, then like for most places, they do all that work directly on the back end. But there may be cases, for example, if like, let's say on the front end, right? That you've got like 10,000 rows of data that you want to render on the page. But then like you have like live updating like implemented on your website. And sometimes like you'll get a live update that says like, hey, in between like position like 95,000 and like 95,001, we want to include like a new row. So now you have to figure out a way to optimally like add that row into the array and then re-render all that information. Re-rendering all that information is completely handled by React. So that part like you don't have to worry about. The only part you do have to worry about is how do you insert that value into the array in an optimal amount of time.
I also kind of don't want to overlook what like Will said here, which is speed doesn't always equal efficiency. Market forces seem to push us towards speed though, and I agree with that because it's like a lot of what we're meant to think of is how to make something more faster, as opposed to like let's say like efficient or have our code be clean, right? Or even like consider memory because we can always buy more memory. We can always fix and refactor the code later, but time is something that we can never get back. But why would that be, right? At least like the way I'm kind of also like digesting like what Will said.
For sure, for sure. It's like that's definitely true. And you can sort of see that with like modern web development right now. Because like you can see like web pages like be like super bloated, right? Like even like the Google like homepage. If we go to say google.com. So it takes like almost no time to load at all. because like Google has optimized for like the speed at which like the page renders. But in terms of how much data is actually like getting like sent over or something like that, we can see that where is it? Where is it? Expand. Size. Star. I wish there was an easy way to just collect all these sizes together. But yeah, the main point that I wanted to make was websites nowadays are like really bloated. That like you'll see like websites take up like hundreds of megabytes of like memory. I wish Chrome could let you see like the amounts, the megabytes of memory you're using. But the general consensus across like most places nowadays is that they do want to optimize for speed, because the research behind it has been that users are more likely to leave your website or to just like not use your website based on like how long it takes for like your website to like respond with data. Like even like fractions of seconds like have like an impact on like maybe a reduction of like 10 to 12% of like your user base. And in fact, I can back this up with data. Relation between page load time and user retention. Yeah, Carlos?
No, I was gonna say to that, it's kind of just like, so it's not even just like market trends, it's like market trends following just kind of maybe how the human component of this works, right? Or like this is how the human brain kind of like works, where it's like, oh, if something's not being given to me quickly enough, then I'll go to something that is like, it's basically kind of like relying like on the dopamine and endorphins that get released in the brain by like clicking on things or being serviced quickly enough.
In a sense, yeah. And yeah, like the research behind it is like even with like yeah, according to Google, 53% of mobile users leave a page if it takes longer than like 3 seconds to load. That's just the way it goes. That if your page takes too long to load, or like if the transitions aren't seamless, then like you're gonna see users like drop off of like your application and like move on to something else, or just give up on like what they're doing entirely. So that's why like even though like the sort of like the balancing like the use of like memory versus balancing the amount of time it takes to run things versus like balancing like the cleanness of like your code, like all those things are important, but in terms of like the market, right? Like the key thing that really does matter to like users and like their willingness to use your site really does come down to like how long it takes your site to load, which like it's not a great like or like an ideal situation, but that is just like the reality of like how it works.
I feel like this is like the zenith of like, we don't make the rules, we just enforce them kind of deal. Where it's
Or
just
it's like we don't make the rules, we just follow them, really.
pretty much, because it's just like, oh yeah, this is just how human beings function, thus we have to follow this path.
Exactly. Yeah, and exactly. Like we've got like some experience from Mikhail here. Like he leaves the site if it takes too long to respond. And yeah, like at this point, like most of us are wired that way. It's just a product of like, like being on the internet. All right. So then if we go back to code here. All right. So that is a linked list here. And then let's say if we wanted to, all right. Okay, and then probably the last thing that we can do for a linked list here is add a way to be able to remove a value. Because like for data structures, for anything that we're really using, like we have to have a way to put values into a data structure, to get values out of a data structure, and to remove values from a data structure, right? So what we can do is we can go ahead and add a remove function of value. And what we'll do is if this .head is equal to null, return. And let me go ahead and comment each line here as well. So let's say if we don't have any nodes, we can't remove anything. If the first node is the one we want to remove, then we're going to set the first node to be the next node, and then we can just stop right there. Otherwise, if the node we want to remove is not the first node, then we start with, again, using the current node, and we're going to iterate our way through until we find it. So while current node.next, we loop through the linked list. If the next value for the current node is equal to the value we want to remove, then we're going to do current node.next is current node.next.next to say we just want to skip over that node. Set the next node to be the one after the one we want to remove, and that's it. And then finally, we just continue iterating. If the next node is not the one we want to remove, then we just keep going. And that is removing a value from a linked list. So let's go ahead and, yeah, Sarah?
I understand line 48. Could you explain line 54 if this dot head dot value is strictly equal to the value?
Yeah, so if the first node is the one we want to remove, then we're just going to say the first node is the one that comes after it.
Sorry. So if the first node is the one we want to remove, then we're just the first one counts as the not that one, but the one after it.
Think of it this way, like if we draw it out again, annotate, do not text, not stamp. Where's shapes? There we go. So I'm not gonna put in numbers for this, just gonna have the blocks. Here's the first node, here's the second node, here's the third node. And if we draw lines, arrows, first node to the second node to the third node, and here's the head at the beginning, right?
Mm.
If the value we wanted to remove was inside of the head node, right? Then all we have to do is say this dot head is equal to this dot head dot next, right?
Yeah.
So this dot head is this first node here right now, right?
Mhm.
What's this dot head dot next?
The one right after it.
Exactly. So all we're doing is we're saying move this arrow over here. Where'd it go? And so because we just moved that arrow over, now the linked list thinks that, hey, this node over here is the first value. And this very first node here is just like off in space, and it's going to get garbage collected at some point.
Gotcha, understood. Thank you.
Yep, no problem. All right, so going to clear drawings here. Okay. So now if we go to perf check here, and let's take a look at the performance for removing a value from a linked list. So here, so we'll push all these values in. Yep. And then let's say, actually we'll do 100,000 here just to not wait too long. And then we'll get rid of the performance here. Well, actually, we should probably just like command exit. Go, then a new line over here. For new dot splice. Actually, I and splice that gray index comma 1. And that's how long it would take to remove all 110,000 items. And then for the linked list, this, that in, remove I. Yep. Okay. So if we try that out now, run it, we'll see that an array takes 11 seconds to run 10,000, and a linked list takes half a second. All right. So we can see that there are definitely improvements that we can make on existing data structures to make it so that, actually, we also maybe want to do one more thing to add something to the end. Linked list here. do we update this to add to end? Actually, yeah, let's finish up with add to end real quick. This dot tail is equal to node, and then node dot next is equal to this dot head. Oh, well, tail is gonna be node. Oh, actually, we don't even need this part here. Because it's always going to add to the beginning. So once we have this dot tail is equal to node there, we're good. And so now here, instead of doing this, we can just do this dot tail dot next is equal to node, then this dot tail is equal to node. So now if we go back to perf check, run this 100,000 times. Oh, well, that's to remove. This, move it down here. This, move it down here. And so now we should see a relative performance improvement for adding a value to the end of a linked list. So if we do node perf check.js, cannot set properties of null, setting next on add to end on line 42. This dot tail dot next at end. And this dot tail, the same node. There we go. Cool. So now we can see that an array, well, actually, an array still takes significantly less time to add something to the end, but a linked list, the performance on a linked list is much improved after adding like a tail, like a pointer to say like, hey, this is going to be a reference to the last item in like the linked list. And we can see that even for like bigger numbers, like a linked list is eventually going to outperform an array. Sarah?
And the reason why that is because it doesn't have to touch every single thing to then add something to the end like it was doing before. We're just going to the tail.
Exactly.
Thank you.
All right. Any other questions? Oh, there is one more thing that we have to do for a linked list. Like we have to be able to like actually step through like all the values. So what we can do is, depending on like how you want to be able to access data in your linked list, whether it's just like getting the first value, getting the last value, or getting like a list of values, you could do something like print current node is equal to this dot head, while current node console.logit, current node is equal to current node dot next. And what this would do is it would just print out all the values in our linked list. So if we were to try and do that here, then move this out here, down there, comment this out, and comment out the array stuff. And we'll say link list dot print. And we'll see how long it takes to print. It's going. About 5,300 seconds or 5,400 versus if we did the same for an array. Move this down here, comment D, uncomment those, and console.log start array. Or actually, we want to loop through each and like yeah, we probably want to loop through each. Actually, no, we can just we'll just go with like console log the whole array. Then uncomment this. Yeah, the time it takes to console log an array, 48 seconds. for or 48 milliseconds. For linked list, about like 5,000 milliseconds. So that's because like an array can be considered like one big thing, and for a linked list, you do have to like loop through each individual value to be able to like print it out. So there are always like costs and benefits to like there are always like trade-offs to like consider when you're trying to think of like, hey, should I use like this data structure or that data structure? And understanding those trade-offs is key to understanding like how you can use data structures or algorithms to improve performance like when you need to. But note that, and I've said this to a couple of fellows before, that premature optimization is the root of all evil. Like that's a relatively famous saying in like computer science, where like if you try and like make things as good as possible right from the get-go, you might end up like pigeonholing yourself into like a really complex situation where you've got like a lot of complexity and like something that isn't working. So you always want to start with having a solution that works and then thinking about like, all right, like how do we optimize this solution that does work? And that's good advice for both on the job when you're like building things and also for when you're doing like technical interviews. Because like at least for like data structures, it's not going to be as common in web development as it is for like across like different development jobs, like let's say like embedded programming or like machine learning, even like, or actually machine learning, it's mainly just like linear algebra. But depending on like what type of like work that you're doing, right, like you may have to employ data structures in order to support like large data sets. And while modern technology helps abstract a lot of like those data structures away, having an understanding of like how to employ these at like what different times would be extremely helpful for making sure that like you're producing like the best performing code. Will?
Would it be helpful to talk about the top 3 algorithms that TikTok uses?
Wait,
In
do they have
regards to what we learned today?
Does TikTok have a list of algorithms they use?
Well, if we can talk about like their top 3 algorithms.
Do you mean the algorithm they use to figure out the top 3, or like how do you mean? Like I haven't used TikTok.
I guess have you used Instagram's version of TikTok? I think it's
I
called.
don't use
forget what it's
social
called.
media. Well, like give me a rundown of like what exactly like is the feature. Like how does it work? What does it do?
Well, cause I'm trying to, because you mentioned algorithms a lot, and I'm trying to figure out what kind of algorithms are being used in some like popular web apps to kind of sink the idea more in regards to data structures.
Gotcha. It's like at least for web apps, more likely than not, if you're talking about top 3 in terms of like what content they're recommending to you, more likely than not, that's a database thing rather than like a direct code thing. That they
Okay.
probably do something like select content where like let's say content match is as close as possible to like the recent content that you've seen. So it might do something like, hey, like if you've been looking at like a lot of programming content and a lot of that programming content has like programming tags on it, then like it might assign a score for programming tags to be like, let's say 1.0. And then like if you like dislike or avoid like a lot of, let's say like give me something you don't like. Is there anything you don't like at all?
Like, I'm trying to think.
Yeah, for sure. Sorry to put you on the comment.
No, it's okay. Yeah, I guess like mean sense of humor, like kids slapping their parents.
Gotcha. So like, let's say like, we'll say like prank videos because like they've gotten pretty wild like over the last few years. So like prank videos like are at like a negative 0.7 to represent like the weight of like how much this content would like fit your like tastes. So based on those values that are ranked, it may pass those values down to like the database level and say like, hey, like select content where like yeah, select content where tags are included in like the positive aspect while like rejecting the tags that are in like the negative aspect as like a very sort of like very, very high level way of like seeing how of like representing that. It could also like grab all content that has like the particular tags that you're looking for and then produces like another ranking based on like if you had like multiple tags that like you were into. Like let's say, I don't know, like programming or
Martial arts.
or yeah, like if you're like following like Lex Friedman or something. Like
Right.
then like that content's going to be like ranked like higher because like you've got like a score of like 1 on programming and you've got a score of like 1 on like martial arts. So any content that has both those tags would have a score of 2, and then it would sort like all content based on like the overall like content match score.
Right. So it seems like, and this is something that I'm still trying to wrap my head around, is that when it comes down to it, computers reduce everything to 0 and 1s in order to read it, process it, and then spit something back out. So even images are reduced to 0 and 1s.
Yep, exactly. I mean, we got time now that like we're done with like the data structures. Would you like a quick rundown on how that works for images?
Yeah, I would love to see that. Yeah.
All right, sure. All right, so just to let everyone know, like that basically concludes like what I wanted to go over for references and data structures. At this point, I'm open to take any open questions on like, hey, how do like particular things work in like on like for files, for what have you, for like networking, like any questions at all like relating to like programming or like the career field, like I'm open to take at this point. But before I get into any of the questions, just a really quick rundown on how images work. Images are broken down into pixels, and each pixel basically has like 4 values that are associated with it, depending on like the type of image. Because like there are JPEGs, there are PNGs, there are like bitmaps, there are a whole bunch of different like image file types out there. But for example, with like PNGs, those have each individual pixel assigned a value of between. So each individual pixel in a JPEG image has 4 values associated with that pixel. The red value, the green value, and the blue value. Red, green, blue, and alpha values. So the RGB that is provided is actually relatively similar to like the hex colors that we use in like CSS. So notice how like in CSS, if we inspect element here, and we did something along the lines of here in element.style, color is hash FF0000, right? And that turns it into red. If we did 00FF, that turns it into green. And if we did 0000FF, that turns it into blue, right? Computers represent colors in terms of R, G, and B because that's generally how like computers are able to like represent colors as a combination of like of red, green, and blue. I think they're called like are they the primary colors? I can't remember. But for images, like they represent each pixel with a number for each red, green, and blue value, as well as a transparency value. So if we did something like opacity like 0.5. Now you can see it's slightly like transparent and it's darker because it's taking on the background color of like the page here. And that's why like PNGs are capable of having like transparent backgrounds so that you can just slap an image onto like a web page or like onto anything you'd like. And rather than having like a white background or a black background, it'll take on the same background as like whatever you're putting that image onto for like in terms of like the transparency. So that's how an image is represented. And beyond that, there are additional like optimizations that each different like image file type uses. So that like not every single like pixel has to have like those like color values. Sometimes there's going to be like a color map, because like maybe some pixels will like share the same color as like other pixels near it. So it'll map like, hey, this pixel corresponds to this color that we're already keeping track of. So that way you only have to keep track of like one color value, and you know that this pixel corresponds to this color that you're already tracking over there. But at its most basic, like pixels are represented with like a red, green, blue, and alpha value. And putting all those values together like would color each pixel on an image like one by one. Does that make sense?
Yeah, it's wild, fantastic. Yeah, pretty dope.
Right, awesome. Then Angel.
Yeah, what you were talking about earlier is, I think, is called sentiment analysis, where you have like a predefined set of like positive or negative tags that you can assign to a bunch of things. So, for example, like let's say you go to a YouTube comment section and it like primarily has words that are predefined as negative, then YouTube will know that, hey, like this content is probably negative, and we may want or not want to push certain things to certain people. But if that negative content has a ton of views, which it usually does, then you can like ship it more to people, and that can kind of like fit into an algorithm. That's like one example that somebody explained to me.
Oh yeah, absolutely, absolutely.
Yeah.
Although one difference between like considering things using tags and measuring things based on like whether you've liked or disliked videos versus like sentiment analysis coming from machine learning is that if you're doing things based on tags and like understanding like what videos you've liked and what videos you haven't liked, the data for whether or not for the weights is actually coming from like your own or like from the user's sort of like input. So you don't necessarily have to like use machine learning to analyze like the text or like the content of the video to understand like whether or not like this is a positive or negative thing, because it's purely based on like the user's reception of the content. Whereas like with sentiment analysis on like text, for example, like if you were to go to Amazon to like do sentiment analysis on like reviews for certain products, that would use machine learning because like it requires like a sort of like going through like each, if not word, then token, and then like associating like each of those like those values, let's just say words for now, with like some score of like, hey, is this positive or negative, just like you were talking about. So that's the key, like that's I think would be the key difference of like one is using like a like the first one of like the TikTok example is using feedback that's already coming from the user in order to define the weights, whereas in the second example with like sentiment analysis on like text is using like data that's already come from like a predefined like set of like learning material for like the machine learning algorithm to be able to process like whether or not like a new set of text that it hasn't seen before has like a positive or negative sentiment. Does that make sense?
Yeah, it does. Also, I didn't like, I guess the possibility is always there for machine learning, but in the example, like I saw it in a YouTube video, person didn't use machine learning. They just use like I guess like a predefined algorithm based on what the like certain, so basically what they did was they used the Reddit API to like scour comments, and they use those comments using, you know, sentiment analysis to see whether comments were positive or negative, and they did like some effect based on whether or not it was positive or negative.
Oh, all right. So
Yeah.
did they have like a preloaded dictionary or something, or?
Yeah, exactly.
Oh, gotcha, gotcha. All right, nice. All right, then Sarah.
So just to kind of go over, I just had a question about the lesson that we did to kind of go over. So just so it's kind of like I kind of understand it like correctly. So with the when we were trying to add it to the beginning of the array, we had to like change all the values one by one, and that's why that was O of what again?
O of n, because the n represents how many items you have in the array.
Got it. Okay. And that took, so when we were trying to put something in the beginning, the array one took a lot longer versus the linked list. But then when we were trying to put it to the end, the linked list thing took was a lot faster because like we took a lot longer because we had to touch every single one of them before we could get to the very end, versus with the array where we could just find it in memory and just push it to the end, right?
Exactly. Because like with an array, we would already know where the array is in memory. And like because they're all like right next to each other, and we also know how many items are in the array already, we can just jump directly down to like the last position in memory where we would want to put our value and then just stick it at that last position.
Gotcha. So that's not so O of the one where we're adding it to the beginning for the array is O of n, and so then by that logic, can we say that when we're adding to the end for linked list, that's O of n as well?
Yep, exactly.
And what's the other of it? So there's O of 1 versus O of n, right?
So far, that's what we've covered. There, like basically any mathematical equation you can plug in could be possible for like the runtime analysis. You could have like n squared, you could have log n, you could have 2 to the power of n, like you could have like m plus n, where like m would be like some other like set of inputs that like might not be related to n. It's like it can get relatively complex, but it all comes down to like reading through the code and like understanding like how many items are being touched and like which items are being touched as part of this algorithm.
Understood. So O of 1 is linear, right?
Yep. Or O of n is linear. O of 1 is constant.
O of 1 is constant, O of n is linear. Gotcha. Thank you.
Yep, no problem. All right. Any other questions? All right. That's basically all I wanted to cover for today, as to not like overload you guys with like too much information, because we did, just to give like a quick overview of like what we just went over. So we went over the concept of what data structures are, did a quick review on, all right, like how do we represent like data in memory? We talked about references and pointers of how we can have pieces, or how we can have like data in our memory actually refer to positions in memory, and how references make use of those like positions in memory to directly like grab the values in memory. We've talked about, yeah, again, like what data structures are as a way of just like organizing data. We've talked about a couple of different data structures. We went a little bit more in depth on stacks. We briefly touched on trees. We quickly covered classes again. We talked about the idea of nodes as classes, as containers for data, and then how to connect nodes to each other in order to form like more complex data structures like linked lists. And then we did a quick analysis on like, hey, like why would we want to use like data structures? Like at what points would we be using data structures versus just like a regular like array or object or linked list or stack or queue? It's like tomorrow we're going to be going over a bunch of different like data structures to understand like, hey, like what are these structures good for, and like how can we use them? And we'll, yeah, like that's basically going to be the game plan for tomorrow, to run through a bunch of different data structures to give you guys some exposure. And then from there, like we'll also be providing some quick little exercises for you guys to work on, like using those data structures as well. All right, Kyron?
Yeah, because I was just about to ask you, like in terms of like all of this stuff, like this data structure and everything that we've been talking about since yesterday. I was like, I know you kind of touched on it a little bit earlier, but it's just like, when will this come into play? I guess that's what you're saying we'll discuss tomorrow.
The main thing is like this will come into play, like you'll actually be using this either in, well, mostly in technical interviews, because like for like even if you're applying for like web development positions, like they really like asking like algorithms questions, like like the Cracking the Coding interview book like has a bunch of things on like data structures and algorithms. And even if you want to like get a job at Google as just like a regular like web developer that does nothing but like do like CSS or something, like you would still have to pass like a technical interview that asks you questions on like data structures in order for like you to be able to like get that position, even if you don't use data structures on a daily, weekly, monthly, or even like yearly basis.
Okay. And then like another question would be like, data structures is more tied in. I think you talked about this or somebody else asked this question. It's more tied into the back end, you said, right?
Mostly. There are potentially cases on the front end if you do want to do like processing of a lot of data on the front end, but for the most part, a lot of like the heavy lifting will be happening on the back end. So that's where data structures would most likely come into play.
Okay. And then when you was talking about like pitches and how it works in terms of like the zeros and ones, actually two questions with that. Sorry, real quick. Like the PNG, you saying those pictures would assume the background of whatever site or whatever yeah, let's say site that you're trying to upload it on.
If it has transparency.
If it have transparency. Oh, okay, and okay, only if it has transparency.
Yep, exactly. Like there should be an image here that I pulled that has a transparent background. If I could find, or actually, me Google PNG transparent background, and go to images. So let's say, for example, this one right here, this butterfly. If we copy the link address, we'll copy the image address. We'll go to, let's say, codepen.io. We'll go ahead and create a new CodePen. Let's just say, go ahead and create a div. Come on. It's class is equal to BG black. Then we'll do like an image. SRC is equal to this image right here. Then dot BG black. Background color black. Oh, it's not actually transparent. Okay, and image with like say 100 pixels, height, auto. Okay, so that image is not actually transparent. So let's find an image that's actually transparent. Actually, why don't we just Adobe make image transparent?
The web, it could be transparent, it could be the web page just as it rendering it as transparent.
Generally speaking, like if it's got like this sort of background, that generally represents that it's supposed to be transparent. And if we were to copy this, because from experience, like that should show up on the web page as like actual like transparency. Like there shouldn't be like the tiled background on it. But let me just like try and make it transparent through like this little tool here first and see if it does the trick. Save image as, come on. Actually, where is it? Oh, Andre, question?
Yeah, I was gonna say with photos off of Google, when you type in transparent background, a lot of the photos are just photos to show you what the transparent background is supposed to look like. So you do have to take it to another website to take the background.
Gotcha. Thank you for that. Okay, so let's go to, did it download it? It did not. Save image as. Come on. Is it doing it? Yeah, it's not doing it. Okay, then we'll go to the terminal and we'll do curl and into bf.png. Okay, open bf.png. Does that do it? It did it. Okay. Then Google Chrome here, and let me plug in my laptop. Come on. Come on. Wait. Then back to Adobe. Come on, Adobe, please. Thank you. I got too much stuff running on my laptop. Come on. You know what? I can't even close all the other tabs because I still have CodePen open.
You guys could touch on this another day. It's gonna take all that. It's gonna take all that.
Yeah, for sure. Let me try this one more thing. It's not even doing that. Come on. Where is which terminal? This one. Open dot. Come on. Come on. Where you at? There you go. Okay. Then that up. Where is the Finder window? Finder with Chrome here. Then really? Documents. There we go. Beautiful. Okay, now it's going to there we go. Then download it, export it, file.png. Yeah, that's right. I can't do this on CodePen now. Yeah, then just real quick, let me just go here. Move, downloads, and what do we call it? File.png. File.png to dot. Real quick, we'll just touch like test.html. Go here, do HTML. Head. There's nothing in the head. Body. Then maybe here we'll do a style tag and do like body, background, color, black, image with 100 pixels, height, auto, image, src is equal to /file.png. And now we can open test.html. That should open up in the browser. And there we go. Now you can see that the butterfly, because it now has a transparent background, instead of having the squares, it just uses the black background.
Okay, cool. And what do you call it? The only PNG you said which what opacity, but not like JPEG.
Yeah, I don't think it works for JPEGs. Like, let me double check that real quick. Do JPEGs have a well, can JPEGs be transparent? I don't think they can, but I'm just double checking. Yeah, JPEGs do not support transparent backgrounds. Instead, they just save them as like having a white background.
Okay. Got it. And last question. You know how we was discussing the colors and before we were talking about like zero, like all things in computers is gonna be based on zeros and ones, right? And then you like you pull up the color and like whatever I forget what you call it when it's like numbers and letters. But hexadecimal, yeah. Why like how would the computer break that down into the 0 and 1 to like
That's a great question. So the numbers and letters that we're using for hexadecimal is
Mhm.
actually a different counting system. Like, you know how like with binary it's base 2 and with decimal it's base 10?
yeah.
Hexadecimal is base 16.
Oh, okay. So that's how they could pull what letters and the numbers, right? I remember you was discussing this before with hexadecimals.
Yep,
So
exactly. So
okay.
if we do something along the lines of like I think we can do parse int like 0x like a. And so if we try to parse in 0xa, like because it is 0x at the beginning, that reads as hexadecimal. So the letter A represents 10 hexadecimal. The letter B represents 11. C represents 12. D represents 13. E represents 14. And F represents 15. And then when we want to go to 16, that would be 1, 0 to say there's 1 16 and 0 like 16s to the power of 1. Or to the power of 0. So there's 1 16 to the power of 1 and 0 16s to the power of like 0.
Was 116 to the power of 0. Okay, that's what the last 2 0, the 1 and then the 0. And then
Exactly.
the 0 and X stands for 0 to the what, 0 power?
0 times 16 to the 0 power. Yep.
0 times 16 to the 0 power.
So if I were to do instead 1F, this would be like 16 plus 15, which would give us, I believe, 31.
Oh, damn, that man, this is a lot of stuff to not say you gotta learn everything, but like if you wanna like know off like the back of your hand, like you gotta keep on messing around with this and to
Yeah,
really
like there's an immense amount of stuff to learn with like in like programming and computer science and like all of that. Like, and there's just like constantly more and more. Like if anything, like computer science is probably like the field that's like advancing the most in terms of science, and like there's just like more and more stuff like coming out like every day. But
that's the crazy part. The what do you call it? The pace of everything is just not gonna change in like next 5 years, it's changing within the next couple of weeks type of thing.
yeah, exactly.
Oh man. All right, that was interesting. Thank you though.
Yeah, no problem. All right, Will.
So there was something that was still I just wasn't catching the idea in my head, and it was that trying to see how the internet connects with my hardware, right? So I put it into Gemini, and it said that its response was that yes, the internet itself doesn't directly access my hardware, but that it does rely on my device's resources to process information and display content. And then it goes on to say that it relies on the device's processing power, graphics capabilities, and memory to function.
Gemini's wrong on that, and also Gemini's not super great. Like,
Okay.
So it does rely on your hardware in the sense that like every computer has some sort of like hardware component that helps it like translate the data that's incoming through like either an Ethernet cable or a Wi-Fi connection and converts that into data that is stored into, I would say, stored into memory. Because like say for example, like we take the example of let's say a web browser, right? That if you've got like an Ethernet cable plugged in, like starting from like the lowest level, what's happening when you have an Ethernet cable plugged into your computer is that there's an electrical signal like going through the Ethernet cable into the Ethernet port, and then from the Ethernet port, it's connected to like other like pieces of hardware on your computer, which link it up into memory. And then from the memory, it's going to try and like take that and like apply it to the application that requested like the data incoming from like from like the stream that's coming from like the internet. So there's definitely a hardware component to connecting to the internet, whether that's like a Ethernet like connector, like let me hardware for Ethernet connection. Yeah, Ethernet card. It's either an
Right.
Ethernet card or like a wireless card, where like a wireless card would have like the different like Wi-Fi standards like available on it, and like it's able to capture a signal that's coming from like a Wi-Fi like router. But yeah, like if we got an Ethernet connection, then like it's a particular like piece of hardware that is able to take in like an Ethernet plug and then like is able to process that input and then send it to like wherever it needs to on your computer. Like I'm not entirely sure of like the whole process like after it gets past the Ethernet card. My assumption is like it goes into memory somewhere and then it figures out how to like pass it to the application, but I'm not like an expert on this particular piece of like of the computer, so I can't say for sure.
So then when it comes to web applications, our limitations truly is based on our network connectivity, right?
I want to say yes, but at the same time, there is the opportunity to have like offline applications where like users would be able to access your site. And then once they access your site for the first time, they have the option to like download basically like a local copy so that like they can still access your site, even though they might not have like an internet connection, but then they won't be able to access the data that they have on like your server if they don't have it downloaded on their computer. So it's like
So it's the same thing like the Git, we do Git clone into our local computer.
exactly. It's like they have a copy of like the site, but like they can't get like the latest updates unless they're connected to the internet.
Interesting. Okay.
Yeah, and that's like a relatively recent development. Like even like I think they call it progressive web apps, or no, using web platform provides a user experience similar to. Yeah, it has to do with like progressive web apps. Like generally these are web apps that are capable of responding to like either like bad internet connections or like no internet connections and can like basically work on your system like and like respond accordingly based on like how good your connection is.
Okay. Yeah, 'cause I'm trying to put everything we learned yesterday and today specifically into web apps. But I think I'm beginning to see like, so the truth of the matter is our web browser doesn't really use our local hardware resources too much.
Oh, it does. It definitely does. Because like in order to draw all these things on the screen, like we've got to pass like the HTML on each of the individual elements through like a graphics like processing thing. It's like
Gotcha.
the question of like how do we get from this to be able to like see what's actually on the page. And so what that means is like we've got the HTML for the layout, which defines like sort of like the different elements on the page. Then we've got the CSS, which defines like what each of the elements looks like. And in order to sort of like combine the two and like process that and have that looking the way that we want to, like we've got to pass both those things through the hardware and like have the system understand like, hey, this is an element and these are the rules for drawing this element, and the browser has specific code that tries to read the HTML and the CSS and then passes that information to like your graphics card to try and
Got it.
that onto like your onto the browser window somewhere.
Got it. Okay, I'm getting it. Thank you.
Yep, no problem. It's like there's always more depth to go into for like every piece that like we see on like in web development. It's like next week when we start talking about like programming languages, we're going to talk a little bit more about like compilers and like interpreters, and specifically tying that back into what we've been doing with like JavaScript and Node.js, where Node.js is like an interpreter. Like it's a program that you run in order to like read the code that you've written so that the computer can understand the code so that it can run it. But yeah, that's a topic that we're going to be covering like next week.
Cool.
All right. Any other questions? Anything else that's burning in you guys' like minds? Right. It's like I said, you guys are free to go. Like, we're basically done with class. I'm just here answering any other like additional questions you guys might have on like how things are connected and all. But yeah. Yeah, I'll stick around in case anyone has any other questions for like office hours or anything. But yeah, you guys are free to go. Have a great night if you guys are signing off.
Thanks, Stephen. Have a good night, everybody.